All right, good evening, everyone. I see there's still some people coming in the back, so please find a seat. It's pretty delightful to see an actual physical room filled with actual physical three-dimensional people, so welcome, welcome. All right, so this is ION GNSS Plus for 2022. I'm Sandy Kennedy. I'm the ION Satellite Division Chair. And I'm opening tonight's meeting as a proxy for Patricia Doherty, who passed away in July of 2022. And I know many of you were personally acquainted with Patricia and her professional accomplishments. And our navigation community continues to mourn her passing, but her legacy will live on in her many altruistic endeavors and good works. So in your on-site program, you'll find a full tribute to Patricia to learn a little bit about her professional career. And I wanted to take a moment here to formally recognize that she's not with us this evening, and the navigation community will definitely miss her. Okay, so moving on to more forward-looking, upbeat things. I'd also like to recognize Dr. Frank Van Diglen, the current ION president, and I'll ask him to do his least favorite thing, which is to stand and be recognized. I'd also like to take a moment to acquaint you with some of the services offered at this year's meeting. For real-time program updates, please access the technical program online at ion.org. And then there is the hard copies of the on-site program for a quick reference and for you to mark up what your plan is for the next 3 days. Virtual presentations and copies of the technical papers presented at this meeting will be available to download through the meeting's virtual portal the day after the author makes it available. So the material on the virtual portal will remain active for 30 days. If a paper is not available online, we recommend you contact the author directly. Give them some motivation to share their work there. And the official conference proceedings and accompanying materials will be distributed to eligible participants in October. So keep an eye out for that. Don't forget, there's Wi-Fi available throughout the hotel, in the public lobby areas, in the meeting rooms here. And the login information is on the cover of your hard copy conference program, but it's really easy to remember. The network and the password is the same. ION GNSS 2020, sorry, just 22, not 2022. Okay. Now on to this year's program committee. First, I'd like to introduce the program chair of the commercial and policy tracks, Dr. Zainab Syed, who is the Senior Director of Regulatory and Quality Compliance for TDK. She was a co-founder and vice president of engineering at Trusted Positioning, Inc. that was acquired by InvenSense. Her current focus is developing and enforcing processes and policies based on IEEE and ISO standards to ensure the highest quality in new and innovative navigation software. To date, Dr. Syed has 10 granted patents, 3 patents pending, a book, over 55 publications, and has implemented several software packages for integrated navigation systems. She was also the recipient of the Early Accomplishment Award from the Association of Professional Engineers and Geoscientists of Alberta, Canada. Dr. Syed, thank you. She has been working with 3 outstanding track chairs with her as well for the commercial and policy tracks. Laura Norman, my colleague at Hexagon Autonomy and Positioning, Dr. Daniele Borio, and I'm looking for you, there you are, with the European Commission, and Dr. Mohammed Kaider from Google. You must be in the front someplace too. Thank you. All right, so in addition to our commercial and policy tracks, we have research tracks chaired by Dr. Matthew Yorger. Dr. Yorger is an assistant professor at Virginia Tech working on high integrity multi-sensor integration for air and land applications. He is a recipient of ION's Parkinson Award in 2009 and the Early Achievement Award in 2014. He is the senior editor on navigation for IEEE TAES and a member of the EU-US ARAM Working Group C and of RTCM's Integrity Monitoring for High Precision Applications, Special Committee 134. He received his PhD from the Illinois Institute of Technology. Dr. Yorger, where are you at? Thank you. Now, he has also had 3 outstanding track chairs assisting him in the research tracks. Dr. Zhen Zhu of East Carolina University, who is unfortunately unable to be with us in person this week. Dr. Zhu's tracks will be handled on site by Dr. Sanjeev Gundawardena of Air Force Institute of Technology. And our second research chair, Dr. Rong Yang of Shanghai Jiao Tong University, was also unable to travel, and her track will be handled on site this week by Dr. Juan Blanc of Stanford University. And finally, in person, Dr. Fabio Dovis of the Politecnico di Torino, who is here in person to recognize. So thank you to that group. So while our in-person attendance is much more than it was in 2021, this is great to look at a room this full this year. We recognize that it was still impossible for many who desired to be here to obtain the travel documentation and authorization necessary. So we extend our gratitude in advance to the chairs that performed peer reviews and those of you who are stepping in to help fulfill on-site responsibilities. So we're happy to report that our on-site attendance is very close to that of 2019 at our pre-pandemic levels. So overall, I'd like to thank the whole program committee. This is a volunteer effort, and it is a lot of work, but not so much work that if any of you are thinking of volunteering, that you should be dissuaded from volunteering in the future. We get really, really great support from the ION staff. Lisa Beatty's team makes the logistics of this disappear, so the program committee can really just focus on the technical details. So thank you to Lisa and all of the ION staff. All right, and then to remind everyone that the Satellite Division recognizes excellence in preparation and presentation of technical papers with the Best Presentation Award. Winners of the Best Presentation Award will be posted to the ION website, so keep an eye out for that, and then it will also be printed in the fall issue of the ION newsletter. So there's always a little bit of bragging rights associated with that, so keep your eye out for who the Best Presentation Awards are. Okay, with our opening business concluded, I would like to move on to our plenary session. And this year we have 2 speakers here in person tonight. And we have a bit of a theme of navigation for exploration in very remote areas. So the 2 kind of remote areas we're talking about tonight is our Earth's oceans, which are 70% of the surface of our planet, but only about 20% of that is actually mapped. And there's a lot of unknown out there still. And there's also a lot of opportunity in how we operate on board the oceans to be more safe and more efficient. So that's our first speaker tonight, Mr. Mike Korotinsky of Ocean Infinity, and then our second remote area of for navigation and exploration that we're talking about tonight is Mars, and we're joined by Dr. Michael McHenry for that. So for format, I will introduce our first speaker. He'll do his presentation. There'll be an opportunity for questions and answers at the end. You'll see a number come up on the screen at some point for our online and in-person attendance that you can text a question to. If you're online, you can also put it into the Zoom chat and it will find its way to me. And if you're in person, there'll also be a mic walking around. No, like a microphone. We'll have 2 mics on the stage later tonight. Anyway, all right. Perfect. Okay, so let me introduce Mike Korotinsky, who has more than 22 years of satellite communications industry experience. He's currently leading a team to integrate satellite and other wireless communications technology into Ocean Infinity's new fleet of uncrewed, low-emission robotic ships called Armada. and those will be remotely controlled from multiple locations around the globe. So Mike will be speaking to us tonight on the application of GNSS for marine robotics. And the stage is yours. Perfect. There you go.
Thank you, Sandy. And you know what? My presentation is not displaying as it should be displaying. Can I get a bit of technical support here? Go through this. It may explain now. I got it. Yeah, thanks. Sorry. It was just the plug was not plugged in early enough. So we have that. Okay, cool. Good evening, everyone. Wow, what a crowd. This looks great. Thank you for joining this session titled Application of GNSS for Marine Robotics. My name is Mike Korotinsky. As Sandy said, I have 22 years in the satellite communications industry. Most of that time leading teams to create products and services that run over satellites. For the past 2 years, I've been working at a company called Ocean Infinity. Now, Ocean Infinity is a marine robotics company. It's a technology company. Our mission is to create and use innovative robotic technology to transform operations at sea, to enable people and the planet to thrive. Innovating to find greener, cleaner, and safer ways of operating at sea has been a driving force behind our business since the very beginning. As Sandy said, we're building a new fleet of lean crewed or no crew at all robotic vessels. These vessels will be navigated and operated remotely on land around the world at remote control centers, thousands of miles away from where the vessel is operating. We're also developing a zero emission marine propulsion system to enable clean fuel operations as we have our fleet operating around the world. With Armada, our greener technology is accelerating the decarbonization at sea. Now, our vessels use underwater vehicles to perform specific operational tasks at sea. Navigating these underwater vehicles present unique challenges that we'll talk about this evening. So let's go. Locating and analyzing undersea assets, inspecting critical infrastructure like pipelines and undersea cables, and completing detailed mapping and survey missions covering vast areas of the seabed. These all require precise navigation, both above and below the sea surface. For navigation, surface vessels supporting these functions use redundant GNSS with augmentations such as differential GNSS. And this is integrated with the vessel's inertial navigation system. We can get about 5 centimeters of position accuracy, a pitch and roll accuracy to about 0.01 of a degree, and heading accuracy to about 0.04 degrees. Now that's all I'm going to talk about surface navigation, because I know you guys know a lot about that. So the rest of the presentation is going to be talking about underwater navigation. So what do the vehicles that operate below the surface most of the time do? Like remotely operating vehicles, ROVs, or autonomous underwater vehicles, or AUVs. Because GNSS signals don't reach very far underwater, precise navigation for those vehicles when they are operating underwater is definitely much more challenging. So ROVs, remotely operated vehicles. ROVs are tethered to our surface vessels, typically with about 3,000 meters of tether, but it can actually have up to 6,000 meters of tether on a vessel with a crew, and we like to call that a crewed vessel. The ROV is operated by a person on that surface vessel, typically with a joystick and a touchscreen. To aid in its navigation for that operator, accelerometers and gyros and pressure sensors are integrated into the ROV. They provide outputs for the operator for vehicle heading, depth, pitch, and roll. Autonomous underwater vehicles, or AUVs, and there's going to be a lot of acronyms, so I'm going to say them and then try to say them again. They're not tethered to a surface vessel. To perform their missions, they're pre-programmed to navigate a specific route, and then they're launched from the surface vessel. When the AUVs are on the surface, they have access to GNSS signals, so they can start positioning themselves. They also synchronize with the surface vessel's clock. But after that AUV descends below the sea surface, those GNSS signals are lost. So underwater, how does an AUV know where it is, where it's going, how fast it's going? How does an AUV stay on course? We're going to find out. Both AUVs and ROVs, they're integrated with an inertial navigation system, or INS. So the INS, it contains high-grade sensors that are used to estimate the vehicle's position and attitude and velocity. In addition to its own sensors, an INS considers navigation aiding from other sources to refine and help correct its estimates. Like I said earlier, on the surface, the AUV can use GNSS, but it actually does is GNSS provides an aiding source to the INS for its navigation. DVL is another aiding source for the INS. DVL stands for Doppler Velocity Logger. DVL uses 4-angled beams, which transmit to the sea bottom, and then it analyzes the phase and amplitude of the return signals to calculate the distance from the seabed, as well as the vehicle's velocity relative to the seabed in X, Y, and Z planes. And this we call bottom tracking. DVL accuracy is dependent upon the frequency that's used for those signals. A higher frequency, like let's say 1200 kilohertz. If you want to get acceptable accuracy out of a DVL using that high frequency, you can only range about 30 meters from the sea bottom. That's not very far. If you use a lower frequency, say 300 hertz, you may not get quite as good accuracy, but it's definitely good enough. But you'll be able to range, that DVL will be able to range to about 200 meters from the seabed. So that's a remarkable thing. So other things that affect DVL is velocity and acceleration. So you can imagine, these autonomous underwater vehicles are moving throughout their mission. They're accelerating, they have velocity, they have acceleration. So that does affect the accuracy. But to give an example, when an AUV is essentially locked in position, so minimum velocity, minimum acceleration, the best case scenarios. This is called station keeping. And with DVL aided INS, an underwater vehicle can achieve station keeping within 1 meter over a 24-hour period. When an AUV is navigating underwater using just this INS and DVL, without any other real-world position references throughout its mission, we call that unsupervised mode of operations. Let's say the AU is performing a survey mission, like you see here. The AUV will navigate to survey a swath of area at a time, and then another swath, and then another swath, and then another one. These swaths all need to be stitched together post-mission to form the final delivery of that navigation survey. So remember, the INS estimates its position, velocity, and attitude based on the sensors, along with help from aiding sources. So INS sensors definitely have gotten more accurate over the years, but they're definitely not perfect. So over a course of a mission, errors will creep in that would cause the AUV to drift off course. The AUV's DVL, the Doppler Velocity Logger, does aid the INS to reduce this drift, but even with a high performance DVL integrated with an INS, when an AUV travels even in a straight line, say about 4 knots, about 7 kilometers an hour, in a straight line, it can still drift 20, 30, even 50 meters every hour. So for short missions, the INS and DVL usually provide enough accuracy so that we can stitch all those swaths of data together to provide the final deliverable for that survey. But what about for longer missions? What about for longer missions that can't tolerate that kind of drift? Now, as I said, an AUV travels about 4 knots or about 7 kilometers per hour. When an AUV executes longer missions, perhaps traveling 500 kilometers over 72 hours, without any other real world references like GNSS during that mission, the AUV really could have drifted kilometers off course. So this kind of drift is unacceptable for us to correct and stitch all that data together, all those swaths of data together. So you might think, why not just program the AUV to surface every once in a while? So let's give that some thought. If an AUV were operating at a typical depth of about 2,000 meters, it would take the AUV about an hour to surface, get its GNSS, get its location, and then it would take about another hour for it to descend back to its operating depth to resume its mission. That 2 hours, that's just not practical. Okay, that's not something we can add to missions. So all during a mission, remember, conventional surface vessels, they're burning fuel. They have people on board that have to be fed and cared for. The time is also important here, but it's not just about that time in terms of surfacing and resuming the mission for the AUV. It's about adding time to the mission, which then would increase the overall carbon footprint left for that mission. So let's talk about another mode of operation to reduce the drift and efficiently support longer missions. We call that supervised mode of operations. And this mode just starts out just like the unsupervised mode. When at the surface, the AUV uses GNSS to update its INS. It synchronizes its internal clock with the surface vessels. As the AUV descends underwater, it loses GNSS signals. But the AVU, for a little while, can still navigate its route for a period of time just using its INS and DVL. So this is where the supervised mode of operations comes in. In a supervised mode of operation, when an AUV is below the surface, the AUV can take INS aiding source, the AUV's INS, can take aiding sources from one other source called ultra short baseline, or USBL, underwater acoustic system. So the AUVs, they have a transponder, and the surface vessel has a transducer that's lowered into the water. And I'm going to use this prop as a transducer. The transducer is a sphere like this, bigger, of course. It has hundreds of elements on it. It sends and receives acoustic signals using the 20 to 30 kilohertz frequency band. Now that's just about above our hearing range, but it's a good thing. There's no dogs around. So initially, what happens is the transducer sends out a number of fixed wide beams to generate an approximate position for the AUV because it doesn't know where it is. It needs to call out. It needs to shout out to the beacon address of the AUV. AUV, where are you? Where are you? Where are you? Where are you? When the AUV hears this, it responds back on a different channel with an acoustic signal as well. Now that signal is received across multiple elements of the transducer. So picture this as the transducer with all the elements. That signal is received just across some of them. So based on the sound velocity in the water, the round trip time, the amplitude of the signal that the transducer receives, and the phase across each one of the transducer that it receives. That transducer that can then focus towards the AUV, narrow its reception beam down to 10 degrees, and optimize directional measurement for range and bearing. So instead of calling out everywhere, it could focus to that AUV for better range and bearing. So using all this information, along with the surface vessel's location from differential GNSS. The surface vessel's USBL system calculates the AUV's position. It then feeds that position to the surface vessel, and we call that a surface-aided position. It feeds it to the AUV along with a timestamp, and that's very important. So it feeds that to the AUV's INS. Now, this may take a second or so because we're talking about acoustic waves underwater. But when the AUV receives this information, it has the knowledge that at that timestamp, when that message was sent, this is where it actually was. It knows that. So along with its aiding information to the INS, like its accelerometers, its Doppler velocity logger, and where it thought it was a timestamp, the AUV's INS can then calculate where it currently is. And then if necessary, the AUV can adjust its heading accordingly to stay on course. So the AUV can continue on its pre-programmed route, surveying, mapping, and inspection. But throughout its mission, throughout the AUV's mission, to keep it from drifting too far away from its course, you would need to periodically locate it. So the surface vessel has to periodically locate the AUV and feed its INS another surface-aided position. And it does this via the supervised mode of operation. So while the surface vessel is there, it's also going to try to get telemetry information from the AUV. How's the AUV working? Can I get maybe a little bit of data from the AUV? But that channel is so small. If you can think back, way back to the 80s, maybe the 70s even, when we had acoustic coupler modems, where we had our first 2400 baud modem or 14.4. Well, that's what we're talking about. We're talking about that kind of speed, right? Because it's all acoustics, all underwater. But it does give us the telemetry. We are able to update the AUV's position, and we're able to get some data. So this is okay, but what if you have to manage, as a surface vessel, multiple AUVs, 5, 10 AUVs? And let's say they're spread kilometers as they're doing their navigation. The challenge is, by the time you go through each one of those AUVs and get back to the first one, that first one could have drifted quite a lot. So let's talk about another way to overcome this challenge. And it's called underwater transponder positioning, or UTP mode. So with this mode of operation, an ROV actually places transponders on the seabed along the line of the AUV's route, or near the line of the AUV's route, if you have multiple AUVs. So each transponder, though, you're just dropping a transponder on the seabed. That position needs to be calibrated before any AUV could even use it to aid its inertial navigation system. So that same USBL system on the surface vessel that's used in the supervised mode of operations, it interrogates each one of those transponders on the seabed. That transponder responds with a reply. And then based on the time for that reply and other factors, the surface vessel's onboard system then can measure that time, right, and compute the range. But in order to derive a more accurate geographic position for the transponder, it doesn't just do this once from one position. The vessel actually performs a box sim procedure. So it does this multiple times from different angles. Once that transponder position then is calculated, the surface vessel then feeds that position down to the transponder. So that transponder says, I know exactly where I am. And that transponder can then be used in the UTP solution. So we can get down to about 3 meters of accuracy at 3,000 meters in positioning these transponders. And if you're just at 500 meters, you can get down to about 0.4 meters, 0.6 meters. So as an AUV is performing its mission, it can range to one or more of these transponders on the seabed. When the AUV can range multiple transponders, that's better. Its INS system can triangulate the distance between itself and the transponders to provide a more accurate aiding source than if only one transponder were used. So I want to make clear, though, that UTP and supervised mode of operations, they do provide similar position accuracy depending upon the number of transponders the AUV can range to. So if it ranges to one transponder, the positioning accuracy is a bit less than with the supervised mode of operations. If it ranges to multiple transponders, the position accuracy is a bit better than supervised mode, but it's pretty close. So the real takeaway here is this is more about efficiency. This is efficiency so that the surface vessel doesn't need to follow around the AVU to update its INS. And let's talk a little bit more about efficiency. That calibration of those transponders, it takes about an hour for each one of those. So it's just not reasonable that you could place enough transponders on the AUV's route so it can range to 3 or more at the same time. So there's a balance here. There's a balance in operating the mission, getting efficient navigation and positioning, and just general operations. So you know that even with one transponder, you can get enough accuracy to be able to stitch all those swaths of data together. But then the surface vessel doesn't have to follow the AUV around. So when it's known that the AUV doesn't need the transponder array, the vessel collects the transponders and then repositions them ahead of the AUV's pre-programmed route. So to perform these missions, everything I've said today, conventional surface vessels burn fuel. They burn fuel like diesel. Support crews. All this has an impact on our environment. So let's talk about a future in maritime navigation. Let's talk about navigating green. Our shipping industry emits 1 billion tons of carbon dioxide every year. There really is an urgent need for accelerated development of zero carbon vessels. One such promising technology is the development of an ammonia maritime propulsion system. That's a clean fuel technology that can eventually power entire fleets of vessels using an innovative ammonia-based fuel cell system. And with the development of new robotic technologies, vessels can be managed and navigated remotely from shore locations around the world using satellite communications and other communication systems for command and control. This would enable fewer and fewer people to be required to be deployed to sea, further reducing our environmental footprint for maritime operations. These vessels would be smaller, cleaner, and safer. Safer because most of the crew would be onshore, not risking their lives offshore. So these capabilities, it's not a pipe dream. They're becoming a reality, but there are many challenges. Let's talk about a few of those challenges. Ammonia propulsion systems, they're still in the demonstration and test phase of development. There's a little ways to go there. Regulators, they've embraced the idea, the concept of reducing a crew on board a vessel, but it'll take some time before they're really comfortable with that concept. Operating a vessel remotely requires you to think about everything that a crew does on board a vessel, everything. Turning off this alarm, flipping this switch, everything, and ensure that it can be done safely and efficiently with little or no crew aboard. This requires new operating procedures and new automation capabilities for equipment that typically is operated by a person on the vessel. All that equipment, everything that people do on that vessel needs to have some automation put in instead of a personnel doing that work. And that needs to then travel over satellite communications to be able to control and command it. So communications here are mission critical between these remotely controlled vessels offshore and onshore remote control centers. In most locations offshore, after about 15 miles from shore, you have to rely on satellite communications, for your data going back and forth. Today, most of those satellite systems that could be used for mission critical vessel navigation, and I want to make that point very clear, mission critical vessel navigation, because this is mission critical. You cannot have that vessel run into anything, and we know that. But most of those systems, they have an inherent latency for data of about 800 milliseconds round trip, because they're in orbit, those satellites in orbit about 36,000 kilometers away from the equator. That's 22,000 miles about away from the equator. So a lot of this latency is due just to the speed of light, the distance to and from the satellite. Now, 800 milliseconds, that's a lot when you're using a joystick to navigate an ROV. Think about it. You move the joystick, you have to wait a second to see that the ROV actually moved where you wanted to and how far it moved. So we're developing new operational procedures, new operational systems and procedures to account for this latency. Now, what's cool is that in a few years, there'll be new satellites that will be available operating closer to the ground. These are called low Earth orbit satellites. And when they mature to be used in mission critical operations, these satellite systems definitely will be able to be used with much less latency, around 100 milliseconds. It's a lot less latency, okay? And that's similar to fiber at a distance. So at Ocean Infinity, we are transforming operations at sea, and we are at the forefront of navigating green. Thank you. Yeah, I'm going to take some water because it's really dry here in Denver.
All right, we've got one question in the room here, so I'll bring it to you.
Thanks. Matteo Luccio, editor-in-chief of GPS World. I know that so far we've surveyed a tiny portion of the world's oceans, but as these bathymetric surveys progress, and we have fairly reliable ocean maps of the ocean bottom, could some version of terrain contour matching be used for navigation of these systems?
That's a good question. There is some terrain matching that is used today. That would be a phenomenal task too of mapping from the ocean, but I think it could be an aid. It could certainly be an aid to navigation.
Oh, good. Oh, you're closer. I'll come to you next.
What about the impact on sea life with all the signals you'll be sending down there?
That's a great question. The frequencies that we are using are pretty good. They're pretty safe, and it's only as powerful as we need them. So that's really important to us, that we don't harm sea life as we operate around the seas.
Yeah, Christoph Günther from German Aerospace Center. Thank you very much for your interesting talk. I had a little bit the same question towards sea life. And when you have 3,000 meters, it's quite a long distance to bridge with acoustic signals. Now, my question would be the following one. When you have these different vehicles operating, they form a sort of swarm. And you could very well have a distance measurement between those at a much lower cost, because it's you can have them operating more closely, and you get a network of those, and they are synchronized, and they can receive the signals and make, for example, detection of direction. And this might be something you could use for in the context of positioning. Is that a
Very interesting. Very interesting. Also, say another thing about frequency, when we talked about the supervised mode with the USBL, we talked about that using frequencies that are just above hearing ranges. So that's actually much safer. but the bandwidths we're using on those channels are really tiny. You're talking about 250 hertz. That's really tiny. So that's going to have less of an impact just because of the frequencies we're using and the channel bandwidth is so small.
Hi, this is Chico from UC Irvine. So I have a questions on the sensor fusion solutions that you're using to aid the inertial navigation system. Have you ever considered using the magnetometer to enhance the heading errors, to bound the heading errors for the inertial navigation system using the magnetometer?
Oh, using a magnetometer.
Uh-huh.
There is a magnetometer as part of the aiding system, but these methods that we have here that we discussed today provide more accuracy than that would, but that is one aiding system.
All right, I've got a couple of questions that have come in through the text there. How much knowledge about water properties that affect acoustic propagation is required to reach a particular navigation accuracy? So I guess
That's a great question. There is something called an error budget that has all the pieces of this that has to be taken into consideration, including the salinity and temperature of the water. So yes, you do need to have a good amount of understanding, but we are required to run these error budgets to make sure that we stay in specifications for our customers.
Actually, that means I have a follow-on question. So do you have sensors on board the AUVs that sense salinity or?
Actually, I don't know the answer to that on
Okay,
the top of my
sorry.
head. I'm thinking they're more on the surface vessel though, for that.
Hi, thank you so much for your presentation. It was very, very interesting. I was wondering if there were limits to depths for the transponders and how you manage that, especially since you're surveying places that you might not know the area of.
So the depths of those transponders are kind of in that 3,000 meter range, sometimes 6,000 meter range. So that is really deep in my mind to be able to get them and fetch them. But they can be fetched with the ROVs, and they still can be aligned by our surface vessels. And that way, make sure that we have that accuracy.
Is it on? Yeah. I'm with the Novatel support team, Zainab speaking. Are you able to simulate any of the missions before launch? Given that your error budget is pretty much unknown, the salinity, the temperature, I don't know, pollution. So are you able to do any simulations before actually dropping the UAVs underground?
Yeah, there is a lot of work that's done before an AUV is launched to make sure that it has its navigation. We have to plan when we're going to visit the AUV. And quite frankly, let's say that AUV goes off and we can't get back to it in time for a long time. We have to program that AUV with a timeout. Surface on its own. So surface on its own. It has an Iridium connection, so it can send data back to us once it's on the surface to find it. But we can do as much as we can do to just simulate and plan, but there's a whole area of mission planning, especially when it comes to AUVs and also with ROVs as well.
This is pretty much an RF navigation crowd you're talking to. And we're all about interference. So I was wondering, when in your signal realm, are there sources of interference? And a related thing, the number one way we get interference is because there's other players. So are you always alone, or are there other people down there?
But the sea is vast, and so far that's been the case where we're alone. But there are cases of interference. So in the UTP solution, when you have the transponders on the seafloor talking with the AUVs, you have to make sure they don't talk at the same time. So they do talk on different channels, so they talk on different frequencies, but if they talk on the same time, there can be some interference at that point. So there's some synchronization that does have to occur there. Yeah. So I'm sure there are some natural sources of interference that may be in, that's okay, some natural sources of interference that may be in the link, but in the, in the error budget, but I'm not familiar with them off the top of my head.
All right, we've had a couple questions come in online. One of them was, are you considering combining acoustics with optics to improve performance?
That's a good question that I'm going to need to take back to my team.
I don't know. You and I were talking about scuba diving before this, and part of the problem when you get deep is it gets real dark.
It does get real dark, doesn't it?
You lose all your color.
So I think some of the questions really has to do with the frequencies that we're talking about. In order to get that accuracy and that depth, that is a balance. The frequencies need to be so much lower.
Right. There was another question here for what the power source for the underwater vessels is today. Is it battery operated for the underwater
Yes,
vessels?
the power source is battery operated, and it is quite a procedure when that AUV comes back on board to change the batteries out.
And that's automated too, right?
That needs to be automated too, yes. And I will say needs to be automated too, quite frankly, because it is quite a challenge to do that.
All right, I see one more. Oh, two more questions. All right, we still have a few more minutes. I think there was also, we'll play the video in the changeover time. So there's a pretty interesting video too that you guys will see next.
Hi there, it's Mira from Helix Geospace. So what's the advantage of actually dropping the transponders to the bottom as opposed to actually having them float and get the GNSS signal directly?
You have to actually know that transponder needs to know its exact position so it can't float. So really it's just more of a receiver transmitter, so that once you send it its position, once you triangulate its position with the box and procedure, then that transponder stays there. It has to stay on a sea surface so that when any AUV comes by, it gets that exact position.
Fixed position, then it's assumed stationary for it. Gotcha. There was another question over here somewhere. Yeah, okay. Can make it.
Hi, I wanted to follow up on is the transponder stationary? Is it assumed stationary? How it takes an hour to calibrate. After that, how often are you talking to transponder in case any currents were to drift it, or is that known?
Yeah, that's a great question. It is critical that transponder is kept at that station. So it cannot move, and based on the currents, we cannot afford for that to move at all.
Oh, there we go. It's just about to say last call, but too soon. Oh, gotta go around.
Todd Kawakami, NGA. I had a quick question. What's the spacing between the transducers and how long does it take to set up a survey?
That is a great question that I don't have the answer to off the top of my head, but if you'd like to give me your name and contact information, I can get back to my team. I know it's going to vary mission by mission. Interestingly enough, it was a question that I fed to the team before I left, but I just didn't get an answer yet. And it was both, how far are they, and how long does it take?
All right. Well, we've given you a workout with the questions.
Yeah, I've enjoyed them. Thank you so
That's
much.
great. All right, thank you. And we'll transition with the video here.
Large-scale commercial ships are operating on our seas. We rely on them for the provision of the materials and goods that we demand for the modern age. Today's maritime transport industry carries over 11 billion tons of cargo each year, representing 80% of all cargo transit across the globe. Operations at sea underpin multiple sectors, ranging from fishing, energy, logistics, and defense. Our shipping industry emits 1 billion tons of carbon dioxide a year, with diesel engines producing 18% of the world's air pollutants. The International Maritime Organization predicts that if our shipping industry continues to expand as it is, emissions will rise by up to 250% by 2050. Our reliance on the maritime industry is only set to grow. Invigorated by the economic rebound from the global pandemic, the requirement for shipping has never been greater. The continuous expansion of the global
Great. Well, now I have an urge to make another joke, which is to infinity and beyond. But anyway, okay, so that transitions us into space. So I'd like to introduce Dr. Michael McHenry from the Jet Propulsion Laboratory. He specializes in autonomous navigation of unmanned ground, seagoing, and space vehicles for both DoD and NASA sponsors, including most recently the Mars rover. Dr. McHenry holds a PhD in computer science from the University of Southern California. Tonight, he's going to be sharing with us the adventures of navigating on Mars. And the floor is yours.
Okay, thanks very much for having me. So putting a rover on a different planet is quite a large team effort. Here is the 2020 team, probably close to its largest. Just for context, my little piece of the 2020 world was really revolved around Perseverance's mobility software. The algorithms, in particular, the autonomous navigation algorithms, and all of the associated system engineering and V&V associated with that. Since the completion of that development and our entry into the operations phase, I'm one of a large cadre of rover planners that are sort of in charge of the rover on a tactical shift day-to-day basis. So we'll start at the beginning on Mars. So where we elected to go after a very long and pronounced series of discussions between different scientific interests is the Jezero crater. And there were a lot of criteria, but at the end of the day, the primary mission of Perseverance is to collect samples that have the capacity to contain evidence of past life. And in particular, the thing that makes Jezero crater appealing is we have very strong reason to believe that billions of years ago, there were large bodies of standing water that basically filled up that crater. And more specifically, the place that this is what it looks like now. The place that the scientists are most interested in is the delta here. So you can see, let's see if I can gesture before it moves on. You can see the incoming tributary, and you can see here this delta looks very much like deltas look like on Earth. That river, that flow in carries materials in the water. It reaches the slower moving water in the lake. They settle out and they produce a delta like this. And those regions are both attractive for the possibility of fostering life and also the preservation of life, that indications of life that we would be able to find now. So this is what it looks like now. No, sorry. So this is the top portion. So that's this up here is the same delta front that I showed you before. And this whole area basically was corresponded fairly closely to the landing ellipse that was sort of our target. But it had, the landing ellipse is large enough to contain most of what you see here. Where we actually landed was in this vicinity across this sort of unusual terrain. We drove south around the corner, north up. We did what we called the toe dip into this region, which we called Seta, which has some interesting geology of its own. We backed out, retraced our path all the way back to the landing site. And about the landing site, all that time we had been progressing relatively slowly, interleaving science, investigations, arm operations, as well as mobility. But when we reached the vicinity of the landing site, we put the pedal to the metal and we basically dedicated all of our power and time to getting to the delta as fast as we could in a period we called rapid traverse. So it's hard to see on the screen, but there are little dots that basically indicate our progress every plan. And in that rapid traverse phase, we covered like 5 kilometers in a month, which by Martian standards is extraordinarily fast. So once we got to the delta, we did a little survey around the most southwestern portion. And then we approached north and spent many months there at the base of the delta collecting the most attractive samples available. Most recently, we started going back to that same location where we did the survey. So when I was putting together the slides, we were at about this vicinity. This was like a week ago, and the rover was poised here on a ripple on our way back to that survey. The ripple has lots of sort of challenges to both the mobility mechanical system and the perception system. But this is what it looks, what I showed you before was in the context of high-rise orbital imagery. This is reflective of the imagery we capture from the rover itself, regenerated into a mesh. And I'll make a call out in this next slide that the institution does a great job in terms of outreach. And so you can, at this URL, you can see all of the latest images that we bring down from Mars at about the same time we see it on the operations team. So it's really fun, and there's a lot of people that participate and watch and ask questions about, in the same day that the latest data came down while we're still analyzing it. But I want to give you some sense of what a Martian vista looks like. So this is just 5 NavCam imagery sort of surveying the horizon here. We're looking across the turret at the other side of the sand dune that we're poised on. Now we're looking over the back of the rover to the expanse, and now we're looking over our right shoulder, and you can see all of these tracks. We've actually traversed this particular area a couple times, so you can see there's a large set of tracks. Very unusual as a rover driver that you see any signs of us going. We don't normally dilly-dally in the same place for this long or repeat ourselves. We produce nice cylindrical mosaics, but what I always really like to do every time they make one of these is sort of zoom into the horizon and just slowly pan across the horizon of Mars. It always gives me this sense that I'm standing there where the rover is perusing the vistas. Okay, but we're not there just to drive around and look around. We're really there to collect those samples. And so this is a representative view of sort of a juicy area of bedrock that is indeed one of the areas that we sampled. This is called Wildcat Ridge. And there's a whole set of operations that go into this sampling operation, which I'm going to breeze through in like 3 slides. But basically we take one of the imaging instruments on the turret and we do a higher res survey by moving the arm over the potential workspace. We get some better images that are used both to assess the geology and the geochemistry on the science side, but on the engineering side, we're evaluating the suitability of all of these rocks for the different sampling tools that may follow if the scientists determine that this is a region worth investigating further. Oftentimes, the next thing we do is we make a little abrasion. So all of Mars is covered in Martian dust. And if you just sort of put your average spectrometer on any particular surface, a lot of what you'll be seeing is the same dust that's relatively evenly distributed across the whole planet. So this is the way. It's basically a small bit that just takes away the weathered portion, and we follow that up with even closer looks up with that same Watson instrument that you saw before. And so if at that point everybody is excited about the prospect of having a sample like this to investigate back on Earth, we'll take a core. So one of the instruments I'll show you a little bit on the rover is actually a drill that collects like pinky-sized rock samples that eventually will return back to the Earth. This tailings pile sort of shows where we just collected a core. Once we get it in hand, so to speak, we image it, confirm that we have something in there, and then in a little magic that I'll show you on the next slide, we confirm the amount of volume that's left in the sample tube, and eventually we'll seal that tube in preparation for its return back to Earth. So here's a very short movie that shows the whole sampling campaign. You can sort of get the magnitude of the arm. you'll see the drill. The drill actually has two browsers that we use to preload. Then the drill feed mechanism actually drills down, takes the core through some mechanical magic, it breaks it off. And then that sample is brought into and docked against what's known as the bit carousel. One of the robots within the robots transfers that sample down into the adaptive caching system, and lo and behold, there's yet another robot here hidden underneath the rover. It takes that tube, puts it through those inspection stations that I showed you, and seals it up and puts it into what's called the parking lot, waiting for us to take the next step to deliver it back to Mars. So popping up now, even bigger picture, Mars 2020 and Perseverance is but one part of a much larger campaign to bring those samples back to Earth. So in 2027, our ESA partners will launch the Earth Return Orbiter. This following year, NASA will launch the Sample Return Lander. One of two things will happen. That lander will either land in the vicinity of an operational Perseverance, or if Perseverance is no longer operational, it will land in the vicinity of a depot, an area on the surface where Perseverance had previously just dropped tubes on the ground. Which of those two will happen is unclear. But if it's the latter, if it's picking up the tubes off the ground, actually the derivatives of the Ingenuity helicopter, which you might have heard about, I'll show you in a little bit, will actually be responsible for retrieving those tubes sitting on the surface of Mars and bringing them back into the workspace of the arm on the lander, so that the lander can, so that those samples are then transferred into the Mars ascent vehicle. So we'll actually launch a rocket from the surface of Mars to put those samples into orbit around Mars. The Earth Return Orbiter will rendezvous with those samples in orbit around Mars and bring those back to Earth. And if all goes according to plan, in about the year 2033, those samples will be returned to Earth, available for all of the intensive investigation that far exceed what we're able to sort of do with the rover mounted instruments. So a brief walkthrough of what's on the rover. So Perseverance is mechanically very similar to the previous and still operating Curiosity rover, which is on a different part of Mars. It's got the same six-wheel rocker bogie suspension, similar remote science mast. One of our upgrades are new engineering cameras. So here on the mast are a set of nav cams, which are sort of our operational cameras. They, as well, there's also front has cameras here mounted on the body that are used for a lot of the arm manipulations. And in the back, there's also a pair of rear has cam stereo pairs. And all of those cameras are now 20 megapixel color cameras, a big upgrade from Curiosity. Back here, you see this little coffee can looking thing is the UHF antenna, and that's used primarily to talk at high rate to one of the relay orbiters around the surface of Mars, which are really critical for us sending the telemetry back from the rover. Back here is the high gain antenna, which is mounted on a pan tilt, so we can point it directly at Earth, and it's critical for receiving the commanding up to the rover that we send generally every day. Inside are a set of IMUs, in particular some LN200s. There's a whole repertoire of amazing science instruments provided by international partners, all of which are remarkable in their own right, but I don't really have time to describe. I'll just, as a short version, say one of my favorite is the French provided SuperCam, which is basically a laser blaster with a co-mounted telescope. And by emitting tiny pulses of laser light and watching the plasma, they're able to do a basic geochemistry assessment even from a distance, without having to park the rover and get out the arm. And so it's a critical part of triaging what it is that is worth the operational commitment to get out the arm and sample. On the turret itself, we have the Sherlock, of which part is Watson, that imager I described. There's an X-ray spectrometer. The GDRT is a can of compressed gas that we use to clear off the tailings when we do an abrasion. There's a touch sensor, and of course the bulk of that is made up by the drill assembly itself. Inside the rover, and I'll go through this quick, I just always really like this picture because it conveys the density and complexity of the avionics that are in the electronics box. But the heart of it, the heart of our primary CPU is our RAD 750. And I want to call out that if you look here at the processing rate of our processor, it's 133 megahertz. So this is basically derived. It is not as fast as this Apple G3 that uses the same process architecture. It's very hard to make a concrete comparison because nobody has benchmarked a processor this old, I think, in 10 years. But it's safe to say that our cell phones are several hundred times more capable computationally than the CPUs on the rover. There are very good reasons why that's the case, but it is a definite challenge for implementing autonomy on the rover. So one big plus up that we managed to get in Perseverance, again, that Curiosity, the other rover doesn't have, is the vision compute element. So it's a sort of dedicated vision coprocessor that's built with the same RAD 750, but also adds a FPGA powered coprocessor card. And so basically we've translated a lot of the compute intensive vision algorithms into the FPGA to help accelerate. And that's, I'll talk a little bit about the benefits that we've redeemed from that. And we brought a helicopter. This is Ingenuity. It's gotten a lot of press. I'm guessing a lot of you have seen it. It was originally just intended as a tech demo. I think they expected it to fly 3 to 5 times. Late last week, they had their 32nd flight, and it managed to survive the winter, even running cold every night because they didn't have enough power for the heaters, but it's still going strong and we're hopeful that it will continue. I'll talk a little bit more about it in a little bit. Okay, so I've been talking for 17 minutes now. I'm finally ready to talk about a little bit of navigation issues. I've set the stage. So I'll talk about a few different, it's kind of a potpourri of navigation problems. I'll talk about something we did during entry, descent, and landing that was critical. I'll talk about how once we land on the surface, we figure out where and how we're pointed. And I'll spend a lot of time talking about how in a day-to-day operation, we get the rover from where it is on Mars to where it is we want it to be on Mars. And if I have time, I'll cover a little bit more about Ingenuity. So this very dense slide that I don't really expect you to be able to see is describing the landing vision system. So it's kind of a truism that planetary scientists always want to go where the terrain is most challenging. It's true for sort of rover mobility. It's also true for landing sites. And this Jezero landing site, in fact, was initially evaluated as too risky to try to land without the addition of this landing vision system. And what this landing vision system does is it provides, during the EDL portion, it provides a refined estimate of where the spacecraft is, followed by a quick analysis by referencing a priori loaded map of where we believe the safe regions are and where are the risky regions. It autonomously chooses the best attainable area and does a divert to that area. And it's hard to see in this picture, but it ended up being crucial. So we made 150 meter magnitude correction to the position that we had sort of that after having suffered the vagaries of EDL, and we ended up making a 600 meter divert to this corner of sort of where it was headed actually for the middle of that SETA region, which as a mobility person would have been terrifying. It's full of these sort of dense sand ripples that are a real problem for navigation. So it really saved our bacon. So that's all I'll say about that. Once we land on the surface on Sol 0, as we call it, immediately after landing, one of the first things we want to do is confirmed that we can establish communication directly from the deep space network here on Earth to the rover on Mars without having to rely on relay through any of the orbiters. And in order to do that, we need to deploy the HTA and get it pointed towards Earth. At this first day, it's the only means we have of assessing our heading really is the IMU. So we do a relatively simple thing. It's not uncommon. We sit and we basically listen or feel the rotation of the planet for some period of time, given that we know the rotation of the planet and approximately where we are, we can back out what our heading is, and we use that to do that initial pointing of the HTA. That was indeed successful. Then one of the next things to be deployed is that mast, and we deploy that mast, and the first thing we do is we point the nav cams towards the sun. So we take a picture of the sun. We know what time it is to good order, and that provides a much more accurate estimate of the heading. There's a refinement that we added around Sol 173 that I'm gonna skip in the interest of time. Okay, so some basics of operation on Mars. So here's Mars with the highlight of the orbiters around the surface that we're really reliant on. But Mars is quite remote. At the one-way light time is anywhere from 5 to 10 minutes. So there is zero prospect of a joystick control of Perseverance. So it is very much more autonomous. As I described, we send the commands once a day. One interesting aspect is that Earthrise is very close to sunrise on Mars. So almost every day on Mars, somewhere between 9 and 11 a.m. is scheduled the uplink of that day's planning, that day's commands for the execution of the rover for that sol. Another thing, another hard constraint of operating a vehicle so far away is on a different planet is Mars day is 40 minutes longer than our Earth day. And so the synchronization between Earth day and Mars day rotates at a cycle that's about every 35 days. And while for the first 3 months we are on Mars time, so we all lived a 24-hour, 40-minute, which is not as much fun as it sounds. Spouses in particular take a pretty dim view of it starting around month 2 in my experience. So we no longer do that, but most weekdays start, and it shifts along that 35-day cycle, somewhere between 6 a.m. to 3 p.m. The tactical team gets down and they look at the latest telemetry that we've received. They work out what the new day's plan is, and they get that up in time for it to be received on the spacecraft by the next Mars morning. All right, so the core to sort of the navigation of the rover is our reliance on the imagery that the rover itself sends back. So basically every drive ends with a panorama of anywhere from 1 to 5 nav cams that would provide a full 360 view of the terrain around the rover. The rover planners, the part of the tactical team responsible for the commanding of the mobility and arms system, they look at that and they can manually identify mobility hazards depending on the resolution that comes down on the terrain, somewhere on the order of 20 to 70 meters. The repertoire of navigation or mobility commands, there's 2 main types. There's these manual driving, where the rover planners are basically in charge of defining fairly precisely where the rover is going to drive. There's also that's composed of either these mob arcs, which are basically just constant curvature arcs of a specified curvature and length, or variety of turn primitives, or there's a basic waypoint navigation in the form of a go-to, where basically we tell the rover we want you to get to this point from where you are. While it's doing that, it is doing a little bit of path selection. So its big advantage is that it's closing the loop on the onboard position estimate, so that if, for instance, as happens, you're driving cross slope and the vehicle is sliding downhill, the rover will be capable of compensating for that itself and getting to the target waypoint. And nowadays, not a big step up from the bad old days of the mirror era, where we just were manually sort of typing in these commands one after the other. We have a nice GUI that lets us basically draw it out, and that tool generates the individual commands used by the spacecraft. But the other half, the more fun half, in my experience, of the means of commanding the rover is with AutoNav. And the big distinction here is that it's that same waypoint navigation, but the rover itself is responsible for using its instruments and imaging to detect and avoid hazards while it's getting to each waypoint. And so the RPs basically lay out a series of waypoints, and the rover autonomously, on a good day, follows that series of waypoints to get to where we'd like it to go. Now, I added this little bit. So obviously, whatever we're doing with respect to the onboard localization is accumulating error as we go. Unfortunately, we have no GNSS system. That would be revolutionary if we did. And in fact, at the end of the day, we rely on a fairly manual process where we take that end of drive imaging, make an ortho-rectified version, and some members of the tactical team, known as localization scientists, basically manually, semi-manually register that data against a orbital map that has been carefully constructed and vetted previously. And with that, basically the focus of the rover planners and their considerations is all done in the current rover reference frame. So I'll talk a little bit about the onboard pose estimation. Frankly, it's a little embarrassing maybe in front of this audience, but the attitude estimation while we're driving is nothing more than our integrating the gyros. We have pretty good gyros, and we didn't really have a feasible alternative. Every time the rover stops, we'll use the Excels and do a nadir update, reestablish gravity, and typically do a sun ID to refine whatever and eliminate whatever heading errors we've accumulated. Position estimation is slightly more complicated, so we basically dead reckon based on the wheel odometry with the 8 Hertz attitude updates, but we also significantly correct it with visual odometry. So image-based frame-to-frame corrections that are critical to us controlling our uncertainty. It's also critical to the safety of the vehicle. Early on in Mars explorations, there were some incidents where we spun the wheel, digging ourselves sort of deeper into sand because we did not have this visual odometry capability. So we had no way, the vehicle had no way of recognizing that the wheels were turning, but it wasn't making any forward progress. Even in Curiosity, because of the computational limitations, they have to basically limit and do slip checks periodically, typically, so they could still turn the wheels considerably. We have the advantage of that vision compute element, which lets us run at a higher rate and basically run every step. So I'm a little behind of target here, so I'm not going to go into the detail here, but the general idea is quite simple. We have the stereo nav cams. We identify the features that we're seeing in the current pair that we saw in the previous pair. We have the stereo calculation that produced the range to all those features. We know we're looking at a rigid body. We can back out the 6 DOF transformation of the camera position between those two. And so we can use that to correct the dead reckoning that we had been doing up until that point. It actually introduces a discontinuity into the pose estimate, but we've written the software carefully to be able to handle that. This is the underpinnings of the stereo calculation. So many of you may be familiar with, but this stereo, it's basically for each pixel in the left image, you're doing a search to find the best corresponding pixel in the right image. We have very good camera models. We know how far apart the cameras are. So basically you have two intersecting rays. You know what the baseline is. It's just a little bit of trig. And we do that across the whole image to produce what corresponds to a range image. We can then take all those range points and translate those into a height map, which is what the vehicle actually uses to assess hazards. So one of the big plus ups that we managed to implement in Perseverance is this new hazard detection algorithm. One of its primary advantages is that it's much more precise than what we had done before. Previously, the Curiosity algorithm basically treats the whole rover as a disk. It simplifies all kinds of things, but it means that if you have two hazards that are closer than 5 meters, the rover is unwilling to thread between them. This technique allows us to do it. It's also great in that it's unambiguously conservative. By looking at what might be under each wheel at a particular evaluation point, we can bound the rover's tilt. What is the maximum wheel drop that could be suffered as you navigate that terrain, as well as what the worst case suspension limits might be. And so I won't go into much detail about the planner. It's a relatively straightforward tree planner. There's not a whole lot of options. In the worst case, we explore about 288 6-meter long paths. In reality, that takes a long time on our processor. And so we have sort of a greedy algorithm that means we only have to do that in the most challenging terrain. So what we end up doing is for each of the prospective paths that we're considering, we do that ACE evaluation every 25 centimeters. As soon as we find a place along that path that looks unsafe, we'll prune that and we'll move on to the next arc. All right, so here is the very first AutoNav drive that we did on the surface of Mars. This one was exciting. So we basically commanded the rover to turn around, face the general direction of the goal, drive 6 meters while initializing the height map that informs the hazard detection. And then we basically said, drive straight to this waypoint that is on the other side of this hazard. We basically dared the rover to hit the hazard. And thankfully it did not. So I'm going to advance this forward in the interest of time. But so here it's completed that what we refer to as driving onto the map. So you can see the height map that has been created during that turn and that drive forward. Now AutoNav knows what's underneath the rover. So we basically bootstrapped AutoNav so it can begin to do its evaluation. Here in this GUI is part of our sort of analytical tool to play back the telemetry. You can see the first set of arcs that it considered in the first step of that AutoNav drive. In actual fact, we set it up so that it made a few steps of progress to the goal before it got within that 6-meter range that it's really considering with respect to the safety of the vehicle. And then as it got further along, you can see it's very faint, but you can see these blue truncated arcs are showing that it considered continuing to drive straight towards the waypoint, but saw that it could not safely do that. And here highlighted is the actual wheel boxes that informed that evaluation at the point that it failed. And so it correctly pruned all of those arcs that were headed onto the rock and started choosing instead the path that circumvents the hazard off to the left of the vehicle. So you can see here it steering to the left of the vehicle, goes on like that. Eventually here at the end, you can see here are the wheel boxes that it considered in the last node of this straightforward arc that it's chosen. And you can see that those wheel boxes just barely skirt the hazard that it picked up in the stereo data, which is what we expect and want it to do. So here's the rest of the drive. As soon as it passes the hazard, then the criteria of arc selection that says get me to the waypoint as fast as you can wins out. And you can see all of the arcs are at this point are evaluated to be safe. We eventually get to the specified distance of the waypoint that we wanted, then resets. It stops at that point so that it can take additional images, what we call the penultimates, because we really like to have images from back a little bit so we can see exactly what's underneath the rover when we stop. It continues on until it again reaches the goal. It then turns towards the desired heading that we specified that's appropriate for comms. In particular, one of the things we always have to worry about is that we need in the next morning or a few mornings afterwards, the head of the RSM not to be between the HGA and the Earth when we're expecting to be able to talk to the spacecraft. Okay, so how is it going generally so far? I say it's going great. The rover is still up and running. We've collected 15 samples, well, 12 rock samples, 2 atmospheric samples, and 1 witness tube, basically a calibration blank that we brought with us. The mobility system has been doing great. Since I made this, I think we have broken the 13 kilometers. Dramatically different from Curiosity is the majority of our driving has been with AutoNav. That's enabled by the fact that we're driving autonomously at about 5 times the speed of Curiosity through some of that software magic, as well as the application of the vision compute element. VO continues to be very reliable, and our longest single sol drive is 320 meters, a Martian record. Our longest single planned drive, so we can break drives across multiple days. This was a weekend drive. We drove 529 meters. I have every reason to believe that we will continue to break those records, particularly once science decides they want to be somewhere else. Okay, so here's last little bit about Ingenuity. So this is flight 12. It's kind of my favorite because Ingenuity, as originally a tech demo, wasn't intended to serve the interests of the project. As a matter of fact, as it proved its merit, the scientists at some point said, we're considering doing this toe dip on the other side of Zeta, but we're not sure that there will be any good sampling areas or that the geology is what we think it is. Can you fly over, survey it, and help us assess whether or not it's worth our investment to drive all the way around and get there? And indeed they did, and we liked what we saw, and we went and successfully sampled there within the interior of Zeta. There's lots of interesting stories about the navigation of Ingenuity that I don't have time to go into, and I'm not necessarily an expert. I will state with some jealousy that they have a Snapdragon gigahertz processor that I would really like to have. Okay, so what's coming up next? So we're going to do our first regolith sample, so that basically that sand sample. We have a special drill bit that's designed specifically to help us collect samples. There's a whole cadre or subdivision of planetary geologists that are really interested about how sand moves around, and so that those samples will also be very valued when they return to Earth. We have lots more exploration of the Delta region. This fall, we will do the initial depot drop, the set of tubes that we will drop very much in the vicinity of where we are now. And eventually, if things go well, we will make our way up the Delta out of the crater and head to the southwest to a whole separate area of geological interest. And of course, bigger picture, it's all focused on bringing those samples back to Earth. And there are some, like I said, there are some many great outreach opportunities. If you go to mars.nasa.gov as a kickoff, it's a great place. You can find 3D visualizations that show you every step of EDL. You can see maps of where every sample that we collected came from. It's super great. And the NASA Persevere is a low bandwidth Twitter channel that shows new and compelling images regularly. And that's all I have to tell you about. Happy to take questions.
The LN200 is one of my favorite IUVs.
Okay, we can share LN200 stories later.
It's just off.
Matteo Lucio, GPS World. For mapping purposes, what kind of grid system do you use and what's the point of origin?
So for planning purposes, the point of origin in the uplink stage is where the rover is currently. And so that's what that team is basically producing for us. It's slightly more complicated in that the rover's reference frame doesn't change with every drive. We have the notion of what we call site frame. And so we will spend some number of days in that same reference frame. It's actually the ground processing tools that lead us to update that about every kilometer. That's the best I can offer you.
How often did the autonomous system make decisions that you think a human could have done better?
Oh, every time the driving gets tough. So when the terrain gets hard, the algorithm by design is focused on being fast and relatively easy terrain. When the terrain gets harder, I refer to it as it flails a little bit. It doesn't have enough global knowledge and it doesn't remember enough of what it saw before. So it has a tendency to dance around a little bit. Another significant limitation is that we do not explicitly detect sand. And so sand normally shows up as unknown terrain in our map. Now we conservatively treat any large enough area of unknown terrain as a hazard because we don't know what's there. We're not willing to put our world resource on assuming that it's benign sand. And so many times, and even just recently, a lot of those tracks that I showed you at that initial panorama, that was because AutoNav was getting a little squirrely because it couldn't successfully range to the sand on the other side of that ripple.
So do those ripples or the tracks, do they become useful features the next time you're in the area?
They're useful at a certain orientation and debilitating in a pathological orientation.
Looking around the room. Okay, so we have a question come in online here. So will future Mars missions use similar navigation technology, or are there plans for new methods that may be considered for next missions?
I'm sure that there will be new navigation algorithms. It's hard to say because it's very hard to convince a mission to take on a piece of new technology unless it's absolutely critical. And so I was very fortunate in that some of this technology, I was part of the technology development before 2020 really existed. So I lived the dream of taking technology development through and fusing it into flight and getting to sort of experience and operate it. But it's not likely to happen again in my career. As far as what that new navigation will have to change, it will be very much mission dependent. It's very focused on and as you can kind of see, it's very driven by the constraints of both the mission and the rest of the vehicle.
I sense that people who, work in your organization have a different sense of urgency about like what career development looks like, because your time scale seems a little bit different.
Yes, I think that's, I think that's right.
All right. Oh, yeah, there's lots of hands. I got to make a choice. Oh, let me go this way.
Hi, Kyle Hauser, University of Minnesota. You mentioned that you're integrating gyros because you have a good gyro, but that also kind of implies that you have a good clock, or at least good knowledge about your clock. Can you talk about how you either update clock biases or just like kind of speak to the quality of some oscillator on board or things like that?
Well, yes. So for integrating the gyros for the purposes of attitude updates during mobility, I think we're not that sensitive to the vagaries of the oscillator. For coordinating the time, and there's lots of scheduling that goes on. For instance, the rover is asleep until it's told to wake up because it's power negative almost all the time that it's awake. And so coordinating those wake up times requires periodic but not very frequent updates to the model of what the delta is between the rover clock and the ground clock.
Hi, talking about LN200 taken from Northrop Grumman. It was not clear if we are using both sun sensors and the HGA to discipline or calibrate the LN200.
So the mobility system does not use a sort of always on sun sensor. We use the nav cams for that. I think it's periodic. We're using the IMUs while the wheels are turning and stopping and taking that sun reference as needed after accumulating a certain propagation time on the IMU. I hope that answered your question. If not, please come back to me afterwards.
Hi, can you use a compass on Mars?
Unfortunately, you cannot. It doesn't. But thankfully, I guess it's also associated with the fact that there's no volcanic activity either. So I guess it's a plus minus.
There was a question that came in online about, well, what kind of rocks? So I think that means, what is the, composition of the rocks? They're similar to Earth, different, can't tell yet because you haven't shifted back.
Well, I'm going to work very hard to stay in my lane as a mobility software person and not a planetary geologist. But I would say generally the planetary geologists use the same languages like mudstones and sandstones that we see here, and the kinds of chemical processes that they observe that sort of concrete that are very similar to what they're used to seeing here on Earth.
So taking it back to localization, a question that came in, since you use cameras for localization, do you face any adversarial scenarios such as fog, dust, all the things that are complicated for cameras?
Yes, definitely. So dust is generally, we have over the course of the missions determined is not a critical problem. We see its impact. We saw its impact in the MER rovers. The nav cams are high enough that they get some level of routine cleaning. So we don't really suffer from that, but there's plenty of other effects. I mean, we're very sensitive to the texture in the terrain. Obviously, we have opposition effect. If you look closely at the pictures, you'll see these new optics we have are great, but they have bad vignetting in that the corners are very dark and we have limited dynamic range. And so we struggle with the balance and fine tuning the exposure to make sure that we're not overexposed in the center, but we have enough signal in the edges to get stereo there. So yes, we struggle with lots of those kinds of things.
So a question here, what prevents you from using a more powerful processor?
Well, bringing in a new processor, a new radiation hard processor is a very intensive and slow operation. In general, it seems like the processors that are vetted to be robust to the radiation environment, beyond low Earth orbit, that those are generally 10 years behind. We're probably another 10 years behind because of our attachment to heritage to the previous Curiosity mission. And it's getting harder, I guess, because there's fewer and fewer people, and the processes are getting smaller and smaller, making them more and more commercial devices, processes more and more susceptible to radiation.
Right. Yeah, I have to say, Frank and I were sitting there and we both looked at what you had for your processing budget for the visual odometry, and we both muttered we had teams that we were going to tell to suck it up from now on. But speaking of commercial components, a question came in here. Are there any plans to implement more commercial components into the rover given Ingenuity's success in this? And if so, what sort of components?
Yes, there's a constant churn and push and pull with respect to what is the right balance. The Ingenuity, of course, had the advantage that technology demonstration task, the freedom to fail, it was not critical in the same way that the first step of this several billion-dollar series of missions. The interesting question will be, what is the policy for those fetch helis that are part of the sample lander? I believe part of that story is the reason that there are 2 helicopters is it's a form of redundancy in part.
Right. Right. Oh, question at the back.
Hi, I was curious about the depots. Do they have transponders on them, or how do you know where they are when you come back in a couple of years to pick them up?
Great question. We are mapping the heck out of where every tube gets dropped, and we have chosen the areas where we plan to drop them very carefully so that we will be able to we will be able to reference the imagery that we use to drop them to finally locate them. And we don't believe that they will be buried in dust in the time, at least at this location. But it's a little bit conjecture because the software and algorithms to do that identification and recovery is yet to be developed. But there's also opportunity for portions of that to be manual. There's a trade-off in terms of how much time you allocate to chasing the tubes down and picking them up, and how much you invest in the autonomy to be able to use the instrumentation that we will collect when we drop them.
Yes, Jed Dennis, and a follow up on that one. I mean, you mentioned earlier that if Perseverance is still operating, then some of the tubes remain in Perseverance and would just be driven back to where the new lander is, or is that how the concept works?
That is correct, and in fact, that's the baseline plan. And more specifically, well, yes, that's the baseline plan.
All right, and I think a last question, because we might be precisely on time with just one more question. How is Mars's orbital satellite position determined? Oh, yes.
I'm sorry, can you repeat it?
Yeah, I will. How is Mars's orbital satellite position determined? Who put that in? Maybe they want to put some more clarification in. I guess maybe for the satellites, like the imaging satellites that they're taking images, are they defined in, I guess, a Mars frame, or how are they positioned? Yeah.
I am not qualified to answer.
Okay, perfect.
Could we have another easy one that I can end on a high note? Because
somebody,
that was
sorry. Oh, perfect. Thank you, Frank.
So I noticed you have latitude, longitude. Where is Greenwich on Mars?
Well, so there's, I made reference to the way we keep track of time on Mars is local mean solar time. And so that's that's reflective of the mean at where we landed on Sol 0. So that's the closest thing to an answer to your question that I can produce.
All right. Well, thank you very much.
Thank you.
Yes. And thank you for everybody attending in person tonight for the plenary session and being such an engaged audience and asking so many questions of both of our speakers. So with that, I'll close the plenary session and I look forward to seeing all of you for the next 3 very stimulating days. All right.